Okay, so last week we discussed the simpler Markov chain Monte Carlo methods and convergence diagnostics for them. And for these simpler methods, then you also implemented Metropolis algorithm, so that you should now kind of have the understanding how going from that you can compute log densities and you are somewhere, and then you can guess around that maybe, since I'm here, maybe there's around here also relevant posterior mass, and we can jump randomly around. But since we are more likely accepting states in higher density, then the random walk eventually takes us where the most of the posterior mass is, and then the chain spends most of the time there. Now in chapter 12, in the beginning sections, there's a bit more about how to make KIP sampler and Metropolis faster, but you can skip these. And then the important part is the Hamiltonian Monte Carlo. And in addition, after the book was published, there has been more advances in improving this Hamiltonian Monte Carlo, and then there's some additional material. It's not necessary that you will go through that extra material on dynamic HMC. I'll go through the main ideas here, but it's good that you at least, on the level I discuss here, you understand also the more advanced things because they are related to some of the HMC-specific convergence diagnostics. And then on the second part of the lecture today, I will talk about STAN. And so the slides then list also this extra material you can use. Mike Betancourt has especially a couple of these really nice videos. One of the listed here. There's also a more recent one, but this is kind of probably the shorter. If I remember correctly, this is the shorter one of those. There are then this the first one, which is the conceptual introduction to Hamiltonian Monte Carlo, goes more in detail and in theory for those who are interested in. And then this Monahan et al. Paper is more easy introduction for applied people, and they had specifically ecology, but it's for other applied people also. Good choice. For STAN, especially the first one is the easiest introduction to the ideas, and then the second one is also still, but a bit more about from the maybe programmer's point of the view. STAN user's guide is the definite information source if you get problems, but it has also a lot of excellent examples, not just function reference. Specifically, the STAN user's guide has a lot of examples you may find useful. And if you like watching videos, I can recommend these Jonah Cabri, Lauren Kennedy videos, which were recorded last year in StanCon Helsinki. And list of demos, so you can find them easier. So in Metropolis, at some point we know that, okay, the density here is this. And then in Metropolis we just randomly guess that, okay, we could go either left or right in 1D or in high dimensions, just somewhere around this point. And since we are here, probably there's something interesting around here. But now with Hamiltonian Monte Carlo, we can often also compute, in addition of the log density, gradient. And then, of course, this gradient tells us additional information that maybe we should actually more likely jump in that direction. There are different algorithms using this gradient information, but then this Hamiltonian Monte Carlo is the kind of the most advanced and which uses it kind of the most efficiently. And it's not just the gradient. As you can see, there's also other things which come from this augmenting the parameter space with momentum variables. Instead of this demo, I'll show you some fancier animations. So you can remember this from last time. So Metropolis randomly jumping around, and there was the problem also how to set the proposal distribution, especially if it's something that there's some dependency in such way that in some directions we would like to jump further away, but in some directions we want to jump shorter. In Hamiltonian Monte Carlo, you can see that it's doing this kind of deterministic dynamic simulation. When we look at this just in this simple Gaussian example, it doesn't look that impressive, but it gives you the idea that it's kind of having a ball, and we have a frictionless ball, and we give it some impulse also, and then it has kinetic energy and it has potential energy, and then in this kind of ball it would go back and forth with certain energy. With certain energy it would also then kind of just go back and forth, and otherwise nothing interesting happens. But with certain rule we sometimes stop and randomize again the kinetic energy, and then it might be that then it would go in a different place. And you can see here at the kind of the initial point, it starts to move in a random direction with random speed, so that the kinetic energy is randomized, and then in this two-dimensional ball it's behaving as this frictionless ball, and that simulation is then based on this Hamiltonian dynamics. What makes it then interesting is that in addition that when I said that when we have the gradient, we would be more likely to go towards where there's more mass. So this, you can think that this pole was now actually negative log density, and the log density in this case would be like this, and then when we exponentiate it, density would have been like this. Of course, anywhere we are, the gradient and the simulation tends that it's often going through the bottom, so spending a lot of time where there's higher mass. But it's not just that. We can see also here, when there are these dependencies, that it can actually travel further away. It's not that it would just want to stay where the highest mass is, but it's also, this simulation makes it avoid very low density regions, and it can now travel much further. You've seen that there's, in these simulations, we are not able to simulate these dynamics exactly, continuously. You can see there are dots connected with lines, and so it is doing discrete step-by-step approximation of that Hamiltonian dynamics. And also one thing is now that then what is the integration time? How long we continue simulation? If we would have a continuous simulation, we would just say that, okay, how long we simulate. When we have discretized this, we can also say how many steps we take. And you can see that if we choose that number of steps badly, I also here mentioned that if we keep simulating, it will go back and forth, and that's not useful. In higher dimensions also you can see that if we have bad choice for the number of steps, we are not actually getting far away. We can actually come back to exactly the same point where we started or very close. So it is also now important to choose how far we go. The new idea was then that try to detect when this simulation is turning back. And then came the name No U-turn sampler. And you can see one simulation here. It can sometimes miss the U-turn, but you can see that it's often now that it's not coming back. You also see here now that it's actually simulating in two directions. Last week I did mention for the Metropolis some of these conditions that how we know that it is Markov chain that has certain target distribution. And in these kind of algorithms which have some adaptive component, like here, that we don't know kind of when to stop, in order that we can maintain that symmetry, that it's as likely from here to end here as it is from here to end here. One easy way is to do the actual simulation in forward in time and backward in time. Or left and right is also possible if we don't want to mix this time thing here. So that's why now it is simulating in different directions. You can see that it's can simulate different amounts, so it is enough that there's some probability that kind of we simulate either left or right. And then if that's balanced, we get this balance also for the possibility of getting back. You can find also so this web page link is in the slides, and from there you get also link to web page which has more of these different simulations, and I'll come back to some of these examples illustrating soon more. So here, this is the same demo example I used last week. This illustrates one nice feature of this HMC, that if this initial point is far away from where the most of the posterior mass is, then specifically the gradient helps a lot to go where most of the mass is. So it's only a few steps that we get there. While we are there, then that simulation helps us to stay in that interesting region. You can see now there are again dots which showing the steps. Now in these simulations so far, there has been quite many of these steps, and now also it is so that each of these dot is one log density evaluation. So we are in these examples making quite many log density evaluations, and I'll come back to kind of the how we can then reduce the number of log density evaluations by making bigger steps, which just make these curves look more clunky. You can also see that the chosen point where it actually jumps is not the end point. And I'll come back to kind of the detail why it is not endpoint in these cases. And you can see that also where even if there's a high dependency, it can quickly move along this narrow path using this simulation and then quickly move around this density. If you remember the trends, these trace plots from the last week, this looks much more kind of noisy. And if we look at the autocorrelation function, autocorrelation goes down much faster. It's around 4, lag 4 that we already have zero autocorrelation. Which means also then that this is then very close to what if we would have independent draws. So I already mentioned that we are kind of simulating the dynamics for some time and then randomizing the direction and speed or the kinetic energy. And this is alternating these two things. And alternating two things then turns out that it then produces draws from the desired target. So we have this step size, which is because we are not able to do continuous simulation of the dynamics. Why it's a parameter is that if the step size is really small, we have accurate simulation of dynamics, but then we're evaluating the energy and the gradient many, many times. If we make step size bigger, we start to have a problem that in this simulation it is kind of, when it goes down, how steep this curve is determines how much there's increase in kinetic energy, and then we should be able to know also what is the potential energy in the end. But if we make too big steps, we start to get error in that we don't know anymore the total energy accurately. We can potential energy we are evaluating, of course, in each point, but we miss that what kind of curve it was along here, and then we get error in total energy. Nice thing is that with small enough step sizes, this error is such that if we think in, so here's 0, and this is in time. When we simulate with small enough step size, this error tends to be such that it increases in time as O1, meaning that even if we simulate very, very long time, the error doesn't increase. This is very nice thing. However, if we make the step size too big, then it is possible that the error explodes. And this, we come back later to that we can try to detect when the error explodes and then based on that find useful so the diagnostics, and we can also use it for the step size adjustment. I also told that, okay, if we have number of steps badly chosen, if it's very small, we don't go really far, and if it's really big, we might get back where we already were. And it's also that if we think about these animations, you can see that when it happens to propose that let's go simulating in that direction where the density is more narrow, it tends to have shorter chains, and when it happens to propose to simulate such that it can go along the density, it's making more steps. And then this is also that it's adaptive all the time. And then it was just that because we have this adaptively deciding that, okay, so we actually do it so that we simulate one step and no U-turn, simulate 2 more steps, and no U-turn, simulate 4 steps, always double the amount added. And of course then also simulating at the same time in the other direction. And if after some doubling we notice that, okay, now there's a U-turn, then stop and then choose the next Markov draw. Now, even if I say that, okay, now the error stays constant if the step size is small enough, we still need to take into account this error. The original Hamiltonian Monte Carlo method used to make it say so that, and it's turned out that kind of that if we make the error so that we get higher energy, we accept, and if we estimate the error so that we get lower energy, we use the Metropolis acceptance rule, whether we accept. And it turns out that this corrects this small error. In the later version of this dynamic Hamiltonian Monte Carlo, it is then, instead of first, so we first simulate in both directions in time, and to take into account the adaptation, we were simulating in both directions, and in addition we need to choose a point randomly, and originally it was chosen uniformly along this path. And so if this was the like t minus 1 point, and then simulating both directions, it was uniformly chosen 1 point along the trajectory, looking at the error and then making this Metropolis decision. The newest version has 2 things differently. One is that it's giving more weight for the parts which are far away from the initial point, which makes it more likely that we get far away. But in addition, it's thinking that what if we average over all possible random choices where to go and consider what's the Metropolis acceptance rate there, and right away compute probability of that each would be selected, and then randomly choose one based on these weights, which has the nice property that it's more likely then to jump somewhere away from the initial point. With this dynamic no U-turn thing, there's also sometimes possibility that we have very small step size, and then we would make lot of energy evaluations and all the time doubling the tree. To keep the computation in control, there's maximum amount of times we double the tree, and this is called maximum tree depth, because it kind of looks like building a tree when we add these additional simulation parts. And then I already mentioned that pick a draw along the trajectory with probabilities adjusted to take into account error in the discretized dynamic simulation. And give bigger weight for tree parts further away to increase probability of jumping further away. These parts, it turns out that it's in some cases making the draws or the Markov chain to have antithetic behavior, so that those odd lag, like first lag autocorrelation, is actually negative. And if you remember that we discussed that for the effective sample size, that we divide the total number of draws by autocorrelation time. But if we have there also negative autocorrelations, it is possible that then this autocorrelation, the time is actually smaller than 1, and we get super efficient draws. I'll show you again a bit of these animations so that you can see. I'll now show you the effect of. So now you can see small step size, very smooth, but now we have a lot of these dots, so that it's making a lot of evaluations, and then we can make step size bigger. You can see that it's still moving around. There's sometimes, if I make this step size too big, we start to get also problems. You can see that it's sometimes not moving anywhere, or there can be these red parts where the error is increased too high. Nice thing is that even if some part of the simulation goes to parts where there's a big error, we can still possibly move nearby. So here you can see the need to adjust the step size. Also then we may have sometimes so that the posterior distribution is very narrow like this, or very narrow like this. And in these cases, the problem is that we need to keep the step size small in order to be able to also move in these directions, and here also, but we would like to make bigger steps in this direction and smaller steps in this direction. And then Stan has in the beginning, so we can do some of the adaptation in the beginning, and then after the initial adaptation we fix some things before we start the actual sampling. So one part is the mass matrix, so that during the initial exploration we already are able to move here somehow, and then we can learn that, oh, it's actually is kind of the longer in this direction than in this direction, or has higher variance in this direction and smaller variance in this direction. And the mass matrix, you can think of it as we would have different step size in each direction, or we are scaling this distribution so that let's scale it so that it looks like this. So we just scale along this axis, make it wider, and in this axis make it a bit narrower, and then it looks like independent, and then it's easy. Same step size is good for every case. If you have dependencies, we need to also learn about this correlation, but we can also, in addition of scaling, do rotation if we learn the full covariance matrix. And this adaptation then makes the final sampling much more efficient. In addition of then kind of doing these scalings and rotations, since these posterior distributions can be also like these bananas, we are not able to just by scaling and rotating make it look like this, or we may have shapes like this. Again, just by scaling and rotating, not possible. But in addition of learning this scaling and rotation, which is kind of easy to learn, it's additionally learning then what would be good step size so that we don't get these explosions in error, and also that we would keep these, because with small step sizes it's also that very small step size the error goes like this, and with moderate it can be that it stays here but doesn't explode, but we still would like to optimize. It's possible to show that for nice distributions certain step size gives certain error rate which optimizes that we will often jump further away. Bigger the error is, more likely it is that we stay where we were or jump smaller distance. And this is the initial adaptation phase, so it's called warm-up. Previously it has been used as the burn-in term when discussing that, okay, the initial points affects the Markov chain and we need to forget the initial point. But now the warm-up also includes this adaptation, and we can do adaptation. So this warm-up sampling is not valid because of the adaptation, but after we stop the adaptation, then rest of the sampling is valid. For example, Stan then has a parameter for this adapt delta parameter, which can control then how big errors we try to get, so that sometimes, because these kind of the optimality criterion holds for nice distributions, and then for non-nice distributions we might sometimes kind of say force the algorithm that will use smaller step sizes that you can go in different places. There was also, I've already mentioned this tree depth and the kind of that we are doubling. That's also one that we can use as a diagnostic, that if we need to use very, very long simulations, it means that step size is kind of small, but it can depend also that in a way our parameterization was such that we were not able to learn good mass matrix, for example. It's also that by default Stan uses diagonal mass matrix, so it does only the scaling, not the rotation. So by default, if you have a posterior distribution which is has a very high dependency, it will scale that it's has the same scale in this direction and this direction, but the dependency remain, and then we have a problem. It's likely that in the future version there will be improved adaptation algorithm which gets faster estimate also for the dependencies, and this is hopefully enabled in January release. I mentioned that if the step size is too big, we may get that error explodes. Now, the difficult distributions are like this, that in some part we would like to have a big step size, and in some part small step size. And these are the kind of likely cases where we see divergences. So when the error explodes, it's called divergence. And sometimes it's possible that we change the adapt delta so that, okay, we accept that we need to use small step size also here in order to be able to also explore here. But sometimes even that doesn't help because this just gets narrower or narrower. Here's an example of sampling from something which looks like this. It's actually in that orientation already, that it's more like this, then getting very narrow. And now then this axis is now the log tau mentioned there, which is, and this is typical in hierarchical models, that this kind of distribution can arise. If we just look at this trace plot with the draws, it doesn't look that bad. There's something kind of suspicious there on the right hand side, that there's a dip and it stays for there some time and then gets back, but maybe it's just slow autocorrelation. But if we actually look at, in this case, how the cumulative mean behaves when we get more and more draws compared to true value, which is dashed line, and the cumulative mean with red, we can see that it seems to have a bias in the estimate, and it's not getting quick enough towards the dashed line. In this case, the problem is that it's this kind of shape. We are getting draws from here, so simulation works here. But when the simulation tries, so it's because it's simulating now with big steps, when it tries to simulate here, it too easily steps out, and the change in density is so quick that the error explodes and we get a divergence. It is now the Stan also then marks those cases when we get error exploding. Instead of just giving up, it marks that, okay, there was this divergence, and then continues sampling. But now you can see here's a plot showing then draws from here, and the green dots are showing where there were divergences, and because they are all in they're kind of in the same region, we are now suspecting that there might be a problem. In this case, this is also on the x-axis, it's just the one dimension from many dimensions, so this is higher dimensional posterior and log tau, and one of the other dimensions where we can see this funnel shape. If we run chain longer, we can also now see this, that it's sometimes sticking in the low values. So sometimes it's able to, that with big steps, it happens to get here, but now it has a difficulty getting out, because if it tries to start simulating in any of these directions, it will fail because the density changes too fast, and only when it proposes that let's simulate in this direction, it can get out from there, but it can get stuck there. even then, running longer, it doesn't solve the problem. So it's just that it's so difficult to get in the low part that there's a bias, but these divergences reveal that, okay, now we have a problem that, and now with the more draws, it's even more obvious that, okay, we are somehow, there's something that makes it really difficult to get further. Making the step size smaller, so there's this delta, adapt delta parameter, making it higher makes step size smaller. You can see that the darker red, now the sampling is able to go a bit further down, but not much. And the reason why, in a way that in here it might look that white was able to go only a bit further, but you now need to remember that this narrow part is actually in 8 dimensions, which makes it more likely that kind of getting stuck there with certain step sizes. And in this case, the solution is that we actually change the parameterization, and we come back to these different parameterizations later. But now the darkest red ones are draws from the true distribution, which then doesn't have the problem to go there, just because we use parameterization where we don't have this funnel shape. I already mentioned several of these kind of problematic cases. Nonlinear dependencies where we have some kind of banana-like shape, which is also was here. It's not enough that we would scale or rotate because of the nonlinear dependency. We still need small step sizes somewhere, which means that it takes more time to get from one end to another end. But with this HMC, we are able to get further. Funnels, I just described that now the optimal step size depends on location, and if that funnel gets narrow enough, we are not able to get there, we get biased results, but these divergences help to detect these. Multimodal, yes. Example here that it's more likely that we stay just in one mode. It's sometimes this is also switching from mode to mode, and in this case these modes are actually quite near, and also in low dimensions like in 2D, it's more likely that we sometimes randomly decide to go far enough somewhere where there's another mode. But if you think that we would have 3 modes in 3-dimensional space, it's more likely that in random direction there's no other mode. So and more dimensions we have, it's smaller probability that we would randomly jump in direction where there's another mode. There are some ways to work with this. And of course, for the convergence diagnostics, it helps that you run several chains. It's more likely then that they end up in different modes, and you at least recognize this. There's possibility of then using tempering methods or coupling of chains methods. And in some types, you could also approximate this with the stacking approach we mentioned in one of our papers. Long-tailed distributions, because of this adaptive integration time in dynamic HMC, it is more likely that also in a way that when it goes to long tail that it then simulates longer and it's more efficient there. there's still efficiency of exploration is reduced, for example, for Cauchy distribution with HMC, but HMC works much better for thick-tailed than, for example, Metropolis. And of course, then we have also difficulties with convergence diagnostics because central limit theorem doesn't hold for mean and variance. And I did last week mention that, okay, we can go instead to ranks, and then that makes it easier. Okay, so this was the first part. Let's have 10-minute break, and then I'll talk about Stan, and of course, any questions? You first, and yes? So now there was different versions of the algorithm also, so that so if we started from here and then we made kind of intermediate steps like this, we could store all of these, but it takes more space, like the memory and disk space, and these are more correlated. And so it is kind of the more efficient that if we just get one draw. It was there's also now different terms. So Hamiltonian Monte Carlo was already from 1980s, and that had that you would have to pre-specify how many steps, and then in the end you would check whether you accept this one based on what's the error in energy, and if you reject that, you will stay here. Then there was a version with the no U-turn sampling version, which added the one that the number of steps is dynamically, adaptively chosen. But already that change made it so that we are not anymore selecting the last one. In that no U-turn sampling approach, we simulate certain time, and then we notice that, okay, now it's starting to getting back. And in order to keep these certain properties that it's still Markov chain which has this specific target distribution, the original NUTS algorithm then chose uniformly one of these points, and in that point, uniformly randomly chosen, check the error in energy and had the Metropolis acceptance step. Then after that, there's also this comes to that kind of the difference in these terms that there's the original HMC is now also called as static HMC because of fixed integration time. NUTS is already a version of dynamic HMC with adaptive integration time. And then the current version of the algorithm, it would be better to call it just dynamic HMC because it's different from the original NUTS paper. And it was doing now two things. One is that it's not anymore uniformly. It favors points which are further away. But in addition, it's not first randomly selecting one point and checking the Metropolis acceptance step, but it's actually kind of computing at the same time what is the probability of choosing one and accepting it. And then it has that weight for each and doing weighted sampling overall. A lot of details. There's more in Mike Bedancourt's paper and videos.